All right, let's talk about a force you are dealing with every single moment of your life, whether you notice it or not. It's this invisible resistance that stops our entire world from just being a chaotic, slippery mess. We're going to dive into the power and, well, the paradox of friction.
And to really get it, let's start with a feeling I know you've had. You're trying to move some heavy piece of furniture, maybe a box. That very first push, it feels almost impossible, right? But then, once you finally get it to budge, it suddenly feels way easier to keep it sliding across the floor. Why is that? The answer to that question is the key to understanding, well, everything about friction.
So, why does that box fight back so hard at the beginning? To figure that out, we have to go deeper. I mean, we need to zoom in, way, way in, to the microscopic level to see the hidden battle that's happening right on the surface itself.
Okay, so this force has a fancy official name: drive friction. The most important thing to get here is that it's a resistance. It always pushes back against the direction you're trying to go. It's kind of like the universe's natural brake pedal, always saying, "Whoa, not so fast."
So where does this friction even come from? Well, this might surprise you. Even a surface that feels totally smooth to your hand, like a polished wood floor, is actually, on a microscopic level, this rugged, jagged landscape. It's full of tiny little mountains and valleys. And when you put two of these surfaces together, all those jagged bits, they just interlock. They grab onto each other and create this really powerful stickiness.
So when you're pushing that box, you're not just pushing, you're actually in the middle of this four-way physics battle. You've got the box's weight from gravity pulling it down. The floor pushes back up with what we call the normal force, keeping it from falling through. And then you have the main event, your push going one way, and that force of friction born from all those interlocking little mountains pushing right back at you.
We know there's a force fighting us, but just how strong is it? Let's figure out exactly what it takes to finally break friction's powerful initial grip. Okay, so you give that box a little shove, let's say with 10 newtons of force. And what does friction do? It pushes back that exactly 10 newtons. The result? A total stalemate. Nothing moves. So you push harder. You double your effort to 20 newtons. And friction? It just matches you. Again, it pushes back with 20 newtons. You can feel the tension, you're straining, but that box is absolutely not going anywhere. This really clever, adaptable opponent, it has a name: static friction. It's static because, well, the object isn't moving. It will perfectly match your push as you ramp up the force. But, and this is the key, its power is not infinite. It has a breaking point.
And that breaking point, it's all determined by something called the coefficient of static friction. Now, that sounds complicated, but just think of it as a grip factor. It's just a number that tells you how much those little microscopic mountains and valleys are digging into each other. A bigger number means more grip, simple as that. And that grip factor, it varies wildly depending on what's touching what. Look at metal on ice. A tiny coefficient, it's super slippery. But wood on wood, whoa, the grip is way, way stronger. This one little number is the reason why sliding an ice cube takes no effort, but sliding a wooden crate is a real workout. So you take that grip factor and combine it with the normal force, which is basically how hard the surfaces are squished together. And that gives you the absolute maximum punch that static friction can throw. This is its final stand. We call it the limiting static frictional force. If your push can just exceed that value, you win. The little peaks break free from each other, and the box finally lurches into motion. And the very instant that box starts to move, something really fascinating happens. The entire nature of that frictional force changes. This right here, this is the aha moment. This is what explains why it's suddenly easier to keep the box going. Just look at this. The moment you overcome that huge initial peak, that breakaway force, which is static friction at its max, the resistance you're fighting suddenly drops. That huge force gets replaced by a smaller, much more consistent sliding force. And that is called kinetic friction. And this isn't just a feeling, it's a fundamental rule of physics. The amount of force you need to start something moving is almost always greater than the force you need to keep it moving. So let's put it all together.
You've basically got two different kinds of friction in this story. Static friction is like a stubborn guard at a gate. It's strong, it's variable, and it matches your force to keep that gate shut. But once you finally break through, you're just dealing with kinetic friction. It's a weaker, constant drag that just resists the sliding. That's the aha moment. You won the really hard part of the battle, and now the rest of the fight is way easier.
So, how much weaker are we talking? Well, a pretty good rule of thumb is that kinetic friction is typically about 25% weaker than the maximum static friction. That sudden 25% drop in the force you have to apply, that's exactly what you feel when that heavy box finally starts to slide.
So we've cracked the case of the moving box. But it's so easy to think of friction as just an obstacle, right? Something that gets in the way and slows us down. The truth is, without it, our world would literally fall apart. Engineers have figured out how to harness this supposedly annoying force and turn it into one of our most essential tools.
I mean, we use friction to our advantage in countless ways. Let's just look at three huge ones: how we use it to lift incredible loads, how we use it to transmit power, and how we use it to, well, hold our entire world together.
First up, the wedge. Like a simple doorstop. You slide it under the door, and the immense friction between the wedge, the door, and the floor creates what we call a self-locking system. It just holds. We use this exact same principle with bigger wedges to lift massive objects, because we know friction will prevent the whole thing from just crashing back down.
Next, think about a belt drive. Your car's engine relies on friction. A rubber belt grips onto different pulleys, and that frictional force is what transfers the engine's rotation to power everything else, like the alternator or the water pump. Without that essential grip, the belt would just slip and absolutely nothing would work.
And finally, my favorite, the humble screw. A screw is really just a ramp, an inclined plane wrapped around a cylinder. The enormous amount of friction along all of those threads is what creates its incredible clamping force. It is friction, pure and simple, that's holding your furniture together, holding up buildings, and fastening our machines.
So the real crucial point here is this. We started this journey seeing friction as the enemy, as the force that stopped our box from moving. But what we found is that it is so much more than that. It's not just about stopping motion. It is the fundamental force that enables control, that gives us grip, and provides structure to our entire engineered world.
So I'll leave you with a final thought. Imagine a world with zero friction. You couldn't walk, cars couldn't drive, the knot in your shoelaces would instantly unravel. Friction might make it hard to push a box across the room, but the real question is, could our world even exist without it? Thanks for watching.